那我要怎么直接做？
没关系，不用，因为你后面其实我们有抓时间，对，你可以连接。
那大家应该知道，我今天要讲的是英文的，希望大家可以承受得住我讲英文。那我们就直接开始好了。Hi everyone and welcome to this section. I'm a little nervous, yeah. For this agenda, I want to design a way that both locals and foreigners can understand, but I think there's no any foreigners, right? Yeah, 都是台湾人，很棒。So I will speak more slowly, but if you don't understand, you can look at the slides to understand what I'm expressing. We run out of time. I might speak faster. It's my pleasure to be here to talk about my research and findings. As far as I know, System Software Track is popular across the club and always attract many attendees. Therefore, I bring a really intriguing topic to the table that's rarely discussed in Taiwan. As you can see on the screen, our topic today is Userspace RCU and how to apply it to a high-frequency trading system. After this section, you will have a solid understanding of how to use it to enhance your systems. I hope you enjoy it. Let me start by introducing myself. I am Jiajun Ye. I'm a software engineer with 6 years of experience. Lately, I've been focusing on back-end development, especially in financial trading. I love it because it comes with many intriguing challenges like performance tuning, concurrency, and low latency technologies, mostly related to CPU architecture and the system software layers. I was the CTO and VP of a startup, and before that, I was the backend developer. I mostly worked in a fast-paced environment with fewer limitations in the paperwork, allowing me to take action directly to keep the team moving in the right direction. I'm currently open to work, so if you have any job opportunities, please feel free to reach out. For more information, such as my resume or LinkedIn profile, you can visit my personal website via the link below. You can also access this presentation there. I will just draw your attention to the overview. We can break the area down into the following fields. First, I will explain some fundamental concepts to ensure everyone has a common understanding. Then, I'll guide you through the implementation details of Userspace RCU. I will also discuss aspects of high-frequency trading and explain why low latency is crucial. To enhance understanding, I will provide a basic example as a case study. Lastly, I will outline some of the challenges we may encounter and conclude with the key takeaways from this presentation. Let's set a stage by discussing some basic concepts. The first thing we should know is what RCU is. RCU stands for Read Copy Update, and is a synchronization mechanism. There's other mechanisms such as spin locks, semiforms, and mutual exclusion. Sorry. RCU is heavily used in the Linux kernel and is optimized for read-mostly scenarios. Readers almost have zero overhead to access data. However, there's no free lunch. The writer has to do more work. For a writer, If it wants to update data, it has to read the old data first, make a copy of the old data, update the data on that copy, and then replace the reference with the updated copy. Additionally, a writer manages all data reclamation. As we know, in C language, we're responsible for memory management. After updating data, the writer should wait until no reader can access the old data and then free the memory. If there is more than one writer, they must coordinate with one another to ensure that only one writer is executing at a time. So let's take a look at key two APIs. Similar to logs, we can use APIs to work with RCU. On the reader side, there are typical log and unlock functions. RCU read log and RCU read unlock. On the writer side, as I mentioned before, it has to wait for all previous readers to ensure that all data cannot be accessed anymore. This waiting period is called a grace period, which I will explain later. In this case, there's a special function called synchronize RCU to wait for readers. If one doesn't want to wait, it can invoke call RCU instead. RCU also comes with two APIs to access data safely. There are RCU assign pointer and RCU dereference. You should use them to avoid memory model related issues. Let's take a look at this graph to understand how RCU works. This graph shows how reader threads and an updated thread interact over time. When a reader needs to read from RCU protected data, it invokes RCU read log, and after finishing its work, it calls RCU read unlock. To safely read the data, the reader also uses RCU dereference. Unlike usual logs, these functions are blocking, which provides better performance for readers. When an updater needs to make changes, it calls synchronize RCU. This function waits until all the reads are done. Some of you may notice a key point. How do we detect when all readers have completed? First, let's look at how our kernel RCU works. Readers has minimal overhead because they only turn interrupts on and off to avoid pausing during critical sections. How can a writer detect a grace period with interrupts? In a nutshell, context switches are key. If a CPU core performs a context switch, it means the reader has finished its task. So a reader raises an interrupt to all CPUs to ensure this happens. We have the same challenge in Userspace RCU, which is detecting the grace period. There's a library called Your RCU that provides 5 implementations for different scenarios. It also has some documentation to explain the concepts. If you are interested, you can visit their website for more information. Now that we've discussed implementations, let's explore when RCU is useful. The slide shows different scenarios. In some cases, RCU is a good fit. RCU is an excellent choice if your application mostly reads data and can accept inconsistency. It will definitely provide great performance. RCU also works well if it requires consistency, even though it may not perform as well as in the previous case. However, if your application has frequent write operation, it may not be the best tool, and you might need to carefully evaluate its performance. This brings us neatly to our next topic, the consistency model. Strong consistency or consistent data means changes are immediately visible to everyone. For example, in a bank account system, any change in the balance is instantly reflected once the customer deposits or withdraws money. In contrast, eventual consistency or inconsistent data means changes are not immediately visible. It takes time for updates to reach everyone. Like with DNS records, the key difference is whether your system can work correctly with outdated data. RCU itself provides eventual consistency. If you need strong consistency, you will have to use other synchronization methods like spin locks along with RCU. Next, let's take a moment to go over implementation. As I mentioned before, there are 5 types of user RCU. There's 5 implementations. Each approach has its own pros and cons. Before using this library, you need to choose the one that best fits your case. Let me explain in more detail. Here's a guide to help you pick the best flavor. If you are building an application and care about speed, QSBR is a good fit. Otherwise, there are 2 cases. If threat management is out of your control, you should choose the bulletproof flavor. If threat management is under your control, there are 3 other flavors available. These scenarios are rare, but you can find more information in the official documentation. Since we are building an application, I chose the QSBR flavor, so I'd like to delve deeper into its algorithm. Its design is quite simple. It defines a special state called a quiescent state. This means the thread has left a critical section and released all pointers to RCU protected data at that moment. To track which threads access the data, every reader has to call RCU registered thread and the RCU unregistered thread. That's a point that we should modify our original code to add these 2 functions to make it work. After that, the read operations could have 0 overhead. However, we need to change the code to make it work. Readers need to call RCU quiescent state periodically. So, how does it work? It maintains a global counter that tracks updates across the whole process. Once the writer updates data, it calls the synchronize RCU function and waits for a condition to be met. The implementation of this function is crucial. First, it increases the global counter by 1, indicating the new grace period has started. Each reader has a local counter that tracks which grace period it is in. If the numbers of the global counter and the local counter and the global counter match, the reader is in the latest grace period. The writer will check these numbers and block until they match. Talk is cheap, so let me show you the code. The RCU quiescent state function does the following. First, it reads the global counter, CTR, into a local variable named GPCTR, which stands for grace period counter. Then, it also reads counter from thread local storage. As you can see, it uses a macro called RCU TLS, which is shorthand for thread local storage. If the counters are already matched, there's nothing to do. Otherwise, it invokes another function. The function simply writes the global counter value into the reader's local counter. It also calls some functions with specific parameters to handle memory modeling issues. You may wonder what URCU QSBR GP is. Here's the definition. It's simply a counter and a few tags. On the right side, the most important function is synchronize RCU. It's a bit complicated, so let's focus on the function wait for readers. Inside the function, it checks each reader's local counter and compares it to the global counter. It only exists when all counters are matched. Now that we'll discuss how RCU works, let's pivot to high-frequency trading. Why is low latency so important in high-frequency trading? It's all about the market timing advantage. Low latency allows traders to act faster than competitors, capturing favorable prices. This leads us to the question, how can we improve it? High latency is usually a major source of time consumption. Following this line of thought, one possible solution is kernel bypass. To speed it up, we often use kernel bypass to handle networking ourselves. Typically, the kernel handles networking from driver to protocol, and users are only responsible for receiving and sending data. With kernel bypass, you can handle data directly from the network interface called buffer. If you want the CPU to handle data actively rather than waiting for an interrupt, we have to implement busy polling. Let's see what we can gain from busy polling. Polling is somewhat like a speed lock. It keeps one CPU core busy all the time. Normally, when the network interface calls receives packets, it notifies the CPU with an interrupt, allowing the CPU to be idle. Handling packets takes time, involving kernel context switches and waking up sleeping processes. By keeping the process busy, you can handle packets as soon as they arrive. However, we need to watch out for some issues in a busy polling process. If we can maintain a steady polling frequency, it may cause issue. First, we need to avoid blocking operations, such as system calls. Then, lock-free operations should be minimized, because they can trigger CPU core-to-core communication, and then we need to offload unnecessary tasks to other threads. These limitations can be challenging for system design. Here's a list of user-level network stakes. There are kernel bypass libraries and implement busy polling inside. As I mentioned before, we have to manage everything, including the TCP/IP stack. These libraries provide the necessary implementations. Open on-load can be run with AFXDP mode. Unfortunately, It's still under development and not yet at release quality. However, it works fine with AMD network interface cards, which were formerly branded as settings, and before that as server flags and server flag. Linux network interface cards can run with their own network stakes called libvna. Both OpenOnBoard and libvna are drop-in representation, drop-in replacement for the kernel socket API. DPDK is an open source option, but it doesn't come with a TCP stack. To address this issue, some developers have published open source TCP stacks that work with DPDK, such as NTCP or C star or FStack. There are many other options. To illustrate the point, let me show a use case. Why do we want to integrate the Userspace RCU in a high-frequency trading system? We will discuss some restrictions of the BD polling system. In this case, URCU is a good fit because it has nearly zero overhead for readers. We also talked about data consistency issue before. Fortunately, those steps are usually asynchronous by nature. In other words, inconsistent data is acceptable. For example, when you place an order to buy the stock, the result usually doesn't come back immediately. You have to wait until the exchange tells you the result of the order. So we can delegate data handling to another thread. We can introduce a logical queue to dispatch tasks to another thread. Once the task is completed, the status will be updated through Userspace RCU or another logical queue, which is checked periodically. By carefully introducing a logical queue, we can remove all traditional locking mechanisms and make the busy polling thread completely wait-free. This is an overview of basic high-frequency trading architecture. It's quite simple. Read market data as quickly as possible. Process it, input it into algorithm, and send trading commands. All of these steps have to be fast. Let's take a look at an example to see how we put it all together. Suppose we have a trading strategy that reads real-time market data and decides whether to trade or stay. Generally, every strategy has limitations. For instance, you can have a maximum position of 2 and a loss limit of $100. We move unnecessary computation tasks to another thread, such as calculating profit and loss or managing positions. This allows the polling thread to process market data as quick as possible, and the algorithms will also be executed in this thread. But how do we update data back to the polling thread with minimal penalty? That's where RCU comes in as a great choice. The only challenge is how to adjust the algorithms to work correctly with RCU. We introduce a derived variable called possible max position. When any order is sent, we treat it as if it will be filled. If not, we fix it when we get a response showing the order has been rejected or cancelled. Profit and loss are also updated with RCU. To simplify the example, we only consider realized profit and loss. The The key to applying RCUs is introducing an increment-only counter variable to maintain data correctness, allowing us to accept an eventual consistency model. If your case can accept eventual consistency, you might need to add other mechanisms such as spin logs or logger queues, although most of them will lower the frequency of the pooling loop. As we come to an end, let's revisit the main points of this talk. HFT applications focus on efficiency, speed, and low latency. Unlike typical network applications that usually focus on high concurrency or throughput. When designing a single thread model, common synchronization methods can block a thread and slow down the performance. Overcoming these limitations can be challenging, especially when introducing RCU atomic operations or lottery data structure. Their downside must be taken into account. If you can manage these challenges, it can provide significant performance benefits. So I think it can be quite a special experience if you take it as an interesting challenge. Additionally, here are some references that help me understand these concepts better. Lastly, I'd like to open the floor for any questions. Feel free to ask anything. Thank you for your attention. May I hear you found this talk helpful?
Do we have any questions from the audience?
可以讲中文，
可以讲中文。
反正没有外国人 OK 啊。
不好意思，我想问个小问题，就是现在你采用的方法是 RCU 嘛？那你有比对过 RCU 跟其他 synchronization strategy 的 performance 会有多少的差异吗？
这样。应该说这个差异没有办法比较，是因为如果你的那个 polling frequency 太低呀、它会直接整个烂掉，因为它那个网路卡的 buffer 如果塞满了，人家后面封包那个就掉到不知道哪里去，就会变成那个 TCP connection 它要重送资料，然后那个速度就会变得很卡，会直接变成我在做一些动作的时候，可能要等好几秒，因为要 TCP 发现那个包不见了，它才会重送，然后就会整个烂掉。所以我们要尽量不要让它卡住，所以那些东西基本上就是用了就会直接烂掉。
你原本的交易演算法里面，你有一个叫 max position， 然后你应用了 RCU 以后，因为它是 eventually consistent， 所以它必须要改变成 possible max position， 是吗？
对。
那个细节可不可以请你再讲一次？
好，假设我们今天要买股票，我买一张台积电，那你这个单子下出去之后，可能要过5秒，它才会告诉你有没有买成功啊，或者是因为你价钱设太低了，所以它直接可能就失败。因为有一种单子是这样，是你下出去，它就会告诉你马上成交，或是马上不成交，但是它是要等的，就不是说我挂上去，然后等人有人下单，然后没有人要跟我买卖的话，那单子就留在那边，然后等我自己在那边。所以，可能有80%的几率就是我们下出去的单子都是会成交的，所以我们就在下出去的当下，我们就预设它已经成交了。简单来讲就是这样。那当我们发现，其实它没有成交，比方说一些特别的因素，比如说可能现在这商品波动太大，让它暂时被退单、暂时不能交易之类的，少数 case， 那我们在那些 case 里面才会去做修正，就是从假设成交变成不成交，把它扣回来。
RCU 在那个交易算法应用的关键。
对，就是应该说我们用了这个 tricky 的方式去让 RCU 的 eventual consistency 可以 work。
Any other questions?
可以再解释一下，我这样回去看
好。
RCU 在这里它解决的那个核心问题。
好，因为是这样，假设我们今天下单出去，我只要花1秒钟来处理好了。但是因为我们处理那个回报回来的结果，就是我今天单子下出去，它告诉我有没有成交的那个结果，它可能很复杂，它可能里面会有一些，比如说 O 的 n 次，有 n 平方的一些演算法，或者是我们在做一些 data lookup 的时候，可能我用了 map， 用了 vector， 用了 array， 所以它需要更长的时间去处理。我们假设处理这个成交结果，我需要5秒，但是因为我今天是一个 single thread 的一个 model， 那因为 busy polling 它的前提要件就是你要是一个 single thread 的 model， 所以如果我把这个成交回报放在我的 polling model 里面处理的话，是不是我会被 block 住5秒？就是我今天那个 market data 进来，它可能每秒会送10笔进来，所以就是每100毫秒1笔。那如果我今天在那个 thread 里面处理那个成交回报，是不是我这中间这5秒的 market data 都 drop 掉，都 lose 掉，都没有办法处理它了？所以我把它移到其他地方去，因为后面的那个计算很复杂，它可能会预算我现在的损益啊，然后一些保证金啊，然后它的很多的 metrics 这样子。
哦，懂，谢谢，懂了。
然后我还有一点没有讲啊，就是我们会稍微去考虑说它的那个 CPU core 里面的 L2 cache 的那个有没有 perform 在里面，因为你如果没有 L2 cache 没有在里面的话，它有时候可能那个 polling thread 它可能又要花更多的时间去 lookup 之类的，但是你今天用了太多的那种容器啊，比如说 binary tree 那种东西啊，就会也会去污染你的那个 data cache 啊，所以我们就希望说尽量把重要的资料都 keep 在那个交易的那个 CPU core 里面，然后它就不用去读取其他的资料，然后造成一些 memory read 上面的损失。
那 high frequency trading 的演算法用 C 写会不会很辛苦？
但是应该几乎都是用 C 写，不然就是要用 FPGA 写。我觉得 FPGA 写会更困难。
所以觉得那个 Go 的 garbage collector 行为还是不够可控，不会用它写 HF 的交易演算法。
你说哪一个？
那个Go。
basically not。对，就算我自己用 C++ 好了，我会把所有的 system call 删掉，包含 memory allocation。所以就是让它几乎全部 keep 住，就是先这些 pre-allocate 好，然后让它 keep 在里面。就是有一些写 C++ 的，他们也有分享过这方面的技巧。那如果这样做之后，其实基本上跟 C 的效能相差不大了，对吧？因为看你写作风格，如果你没有写的很乱七八糟的话，其实 C++ 跟 C 的差异是可以几乎没有的。
所以会有这样的考量，是因为去分析过，就是它 I/O 棒跟那个 CPU 棒的那个 cost 是 CPU 棒这边会比较大。
CPU 棒其实比较小，因为大部分是卡在 I/O 啊。如果我 CPU 算，可能我只要算以人类时间来算，可能算1秒钟，但是我那个 I/O 网络的 latency 可能会是10秒钟或50秒钟。所以倒也不是 CPU 棒的问题，而是我尽可能是希望去缩短它。
当时跟交易所之间的网络连线是专线特别近啊。当时跟交易所间的 latency 大概多少 ？Roger。
这个你看城市交易的某些 YouTuber 他们都会讲，但是基本上台湾是不行的啦。就是台湾如果你做这件事，你要透过券商或期货商，就是你要大概拿个3亿台币出来，然后跟他们请一个交易营业的牌照，你才能这样做。 但国外就没有这些事。
那真的用到 equity trading 的时候，比较是在传统金融，不是在 crypto 加密货币那边的时候。
crypto 也可以用，但 crypto 我个人觉得效益不大，就是这样，因为它是云端机房嘛，所以能做的事情大概就是跟云端机房摆的特别近，但是你基本上还是要走网际网路。但传统的话是可以 co-location 进去的，就是可以更近的。好，放在会示范。
好，大家谢谢。